A honeybee colony does not swarm without warning. It prepares. For at least 72 hours before the first bees leave the hive, the colony undergoes a measurable biological transformation, one that experienced 19th-century beekeepers learned to recognize, read, and interrupt. The swarm does not begin when bees leave the entrance. It begins 3 days before, in the quiet architecture of the brood nest. This is the biological reality that separated productive apiaries from broken ones in the era before modern management systems. Not equipment, not chemical intervention, observation timing. Have you experienced this in your own hives? A swarm that seemed to come from nowhere, leaving behind a suddenly depleted colony. Leave a comment below describing what you saw in the hours before it happened. If this channel's approach to colony biology is useful to you, a like helps this content reach other beekeepers who think the same way. Here is what makes this window both critical and easy to misread. The behaviors that signal it are not dramatic. They are subtle. A slight reduction in forager exit traffic at the entrance in the early morning. An unusual stillness in the hive that registers as calm, but is not calm at all. And deep in the brood nest, sealed queen cells already capped, already counting down, marking a biological clock that most beekeepers never learn to check. By the time most beekeepers recognize a swarm is coming, the biological countdown has already been running for days. Beekeepers of the late 19th century, men like Moses Quinby, whose practical work in New York State shaped American apiculture before Langstroth's movable frame was widely adopted, and Charles Dadant, whose colony management writings in the Illinois tradition emphasized reading colony state rather than reacting to colony events. These practitioners developed a vocabulary for what swarm preparation looked like from the outside, not because they had better equipment, because they had better observation schedules and a clearer understanding of the developmental biology driving the process. What most beekeepers misunderstand is this: the 72-hour window is not a window of swarm prevention in the conventional sense. It is a window of biological redirection. The colony is not still deciding to swarm during those 72 hours. It has already decided. What remains undetermined and what is still biologically influenceable is whether the energy the colony has invested in sealed queen cells will produce a swarm departure or become the raw material of a controlled split. The difference is narrow and it closes fast. To understand what makes this window real and actionable, it is necessary to understand the sequence of events that precedes it. Swarm preparation in a honeybee colony does not begin with queen cells. It begins weeks earlier with a demographic shift in the nurse bee population. As the colony builds through late spring, nurse bee numbers increase faster than available brood to feed. This surplus of nurse bees creates a hormonal condition in the colony, specifically, a reduction in the effective distribution of queen mandibular pheromone across the worker population. When the colony grows large enough that pheromone distribution thins at the periphery, queen cup construction begins. These cups sit empty at first, positioned along the lower margins of frames, where wax production is highest. The presence of cups alone is not an emergency. It is a signal to watch. The escalation happens when the queen lays into those cups. From that moment, the developmental clock runs independently of beekeeper awareness. A queen cell requires 16 days from egg to emergence. The swarm does not wait for emergence. In documented colony behavior across multiple sources from the late 19th and early 20th century, swarm departure typically occurs on or around the day the first queen cell is capped, approximately day 8 from the egg. This is the entry point of the 72-hour window. The colony does not wait for inspection day. The window does not wait for convenient weather. When the first queen cell caps, the colony's behavioral architecture changes measurably. The laying queen, who has already been fed less by attendant workers in the preceding days, begins to physically reduce. Her abdomen decreases in mass as workers shift from nutritive support to pre-flight conditioning. At the same time, a subset of workers begins consuming honey in quantities noticeably higher than normal brood-rearing requirements. These are the swarm cohort, workers and scouts loading fuel reserves for departure. The clustering behavior at the entrance shifts in character, not a bearding response to heat, but an aggregation of transition. The 72-hour window begins at first capping. The swarm cohort assembles. The queen reduces. The colony waits for appropriate weather. This is the moment. Not before, not after. Here is the timing risk that collapsed productive colonies across 19th century American apiaries. Beekeepers who inspected on 7-day schedules missed this window entirely. A colony inspected on Sunday with unsealed queen cells in active development was a colony that could produce capped cells by Tuesday and swarm by Wednesday or Thursday, well before the next scheduled inspection. The 72-hour window fell entirely between observation cycles. Langstroth himself wrote about the consequences of infrequent inspection during swarm season, not as a moral failure, but as a structural problem in how beekeepers had been trained to think about time. The hive does not operate on a human calendar. It operates on a developmental one. Now to the practical method itself and the precise sequencing that made it functional. Confirmation of the window required a specific identification skill, distinguishing freshly capped queen cells from capped drone cells by their profile. A queen cell projects from the comb surface in an elongated peanut-like form, with a textured wax cap that is newer and paler than surrounding comb. It is typically positioned at the lower margin of the frame, where brood comb meets open comb or the frame's wooden bottom bar. A beekeeper who could identify a freshly capped cell, smooth, new wax, elongated shape, lower frame edge positioning, had confirmed entry into the window. That identification was the trigger for a structured three-part response. The first step was brood nest space assessment. At the moment of confirmed queen cell capping, the congestion state of the brood nest determined everything that followed. If the colony had open-drawn frames above the brood cluster, comb accessible for egg-laying expansion, the congestion-driving swarm behavior could still be interrupted. If there was no open space, and the queen had been running out of laying room for 7 to 10 days or more, the colony's swarm impulse was significantly harder to redirect. The window remained open, but the biological momentum was steeper. The practical measurement these practitioners worked with was direct and specific. If fewer than 3 drawn frames above the brood cluster showed open, accessible space for queen expansion, the colony was in active congestion. The immediate response was to open that space, not by adding a super above a queen excluder, not by placing frames at the outer edges of an upper box in cold weather, but by inserting drawn comb directly into the brood nest's thermal zone, frames placed adjacent to the outermost brood frames, where the queen could access them without crossing cold air. Temperature was not incidental here. In early spring swarm season, when nighttime temperatures still dropped below 50 degrees Fahrenheit, placing new frames too far outside the cluster's edge created an expansion gap the colony could not bridge thermally. Workers would not move the cluster into space that was cold. The frames had to be inserted within the warmth, typically 1 to 2 positions inward from the outer brood frame, close enough that the queen encountered them during normal brood expansion. The second step was selective queen cell management, and this is where early practice diverged most sharply from the reactive approach of destroying all visible queen cells. Removing every queen cell indiscriminately, an approach that became common as beekeeping industrialized, often triggered emergency cell construction on whatever larvae were young enough to be converted, producing lower quality queens on an unpredictable secondary timeline. The historical protocol was selective retention. Identify the 2 best-formed, most recently capped cells, retain 1, remove all others systematically. The retained cell served as biological insurance against accidental queen loss during the manipulation, while the removal of excess cells reduced the colony's own hormonal reading of swarm saturation. A colony maintaining 1 sealed queen cell does not sustain swarm momentum the same way a colony with 7 or 10 active cells does. Strong colony, fewer cells, redirectable energy. The third step was the most timing-sensitive of all. A direct assessment of the laying queen's physical condition. A queen who had already undergone significant abdominal reduction, visibly slimmer than her normal laying season profile, moving rapidly across the comb rather than in the deliberate egg-laying pattern of a productive queen, was a queen already in pre-flight preparation. Her workers would show a corresponding shift in attendance behavior, fewer bees in the close retinue formation associated with active laying support. A colony with a queen in this physical state, regardless of how well the beekeeper managed brood nest space and queen cells, carried higher biological momentum toward departure. The intervention could still delay. It could still redirect. But the condition required acknowledgement and a modified response. For colonies where the queen appeared already reduced, practitioners in the Dadant tradition recommended a proactive split rather than space-based intervention alone. The protocol was direct. Remove the old queen and a portion of adult bees along with frames of open brood into a new nucleus box. Leave the parent colony with the single retained, sealed queen cell. The split satisfied the colony's reproductive drive while converting an uncontrolled population loss into a managed division. The parent colony retained its location, its forager force, and its active brood. The split, given a sealed cell, would produce an emerged virgin queen in 7 to 9 additional days and begin laying within 3 to 4 weeks. Here is what makes this approach biologically coherent, rather than merely traditional. The swarm impulse is not a colony malfunction. It is the colony's primary reproductive success mechanism. Every colony that swarmed successfully was, from an evolutionary standpoint, a colony that achieved reproduction. The 19th century insight was not to suppress this mechanism, which tends to produce erratic, often counterproductive results, but to redirect its energy, to honor the colony's demographic pressure through managed division rather than forcing suppression through cell destruction and space management alone. This reframing is not trivial. A beekeeper who approaches the 72-hour window as a problem to eliminate applies different interventions than a beekeeper who approaches it as reproductive energy to redirect. The results over an entire swarm season reflect that difference measurably. If you value biology-based beekeeping, consider subscribing. 2 consistent mistakes undermined this protocol in practice. The first was intervening too early, acting on queen cup presence before capping was confirmed. Beekeepers who restructured the brood nest and removed cups in response to cup production alone frequently destabilized colonies that had no immediate swarm intention. Queen cup production is a normal feature of a healthy colony in active buildup. It is not the intervention trigger. Confirmed capping of the first cell is the trigger. That distinction matters. The second mistake was addressing space expansion without a thorough queen cell census conducted in the same inspection. Adding frames to relieve congestion while leaving 7 capped queen cells in the brood nest accomplished little. The 2 elements, space and cell management, had to be executed together, within the same session, within the same biological window. The seasonal boundary of this protocol deserves explicit attention. The relevant window runs from the first warm week of genuine nectar flow conditions, typically when fruit trees are in late bloom and dandelion is fully active, through the summer solstice. In the northern tier of American beekeeping territory, this means late April through mid to late June. After the solstice, swarm impulse drops sharply in most temperate zone colonies. Colonies that have not swarmed by late June are unlikely to do so that season. The 6-week window centered on the nectar flow buildup is where the 72-hour protocol applies. And here is the practical constraint that the entire method ultimately depends on: inspection frequency during that 6-week period. The 72-hour window requires detection. Detection requires inspection. A beekeeper inspecting every 7 days during peak swarm season in late April and May is structurally unable to catch this window with consistency. Early practitioners who applied this system successfully typically inspected colonies showing strong buildup, high nurse bee density, and active queen cup development every 3 to 4 days during that concentrated period. Not every colony, every day. High-priority colonies, the strongest builders, the most congested brood nests, received the shortened interval. That was the operational commitment the method required. The biology set the schedule, not the beekeeper's convenience. Colonies managed through this protocol did not uniformly avoid swarming. Biological systems do not produce uniform outcomes. What the approach stabilized was the ratio of controlled events to uncontrolled ones. Apiaries that integrated 72-hour observation and intervention reduced their unmanaged population losses. They converted a measurable portion of what would have been field swarms, colonies lost to trees and fence posts and neighboring gardens, into managed splits that expanded the apiary rather than depleting it. The outcome was consistency and reduced loss over a season, not the elimination of the swarm impulse from the biology of the colony. A secondary benefit that practitioners noted consistently was the forager retention effect. A colony that passed through the 72-hour window without departure because congestion was relieved, excess cells were removed, and the swarm cohort was reintegrated into normal colony function, retained its experienced forager population intact. That colony entered the main nectar flow with full population density. The surplus distinction between colonies that swarmed just before a major flow and those that were redirected in time was visible in the honey harvest, not as a dramatic doubling, but as a consistent stabilization of surplus production across the season. The honeybee colony preparing to swarm is not malfunctioning. It is succeeding at reproduction. The 72-hour window that precedes departure is the colony's biological announcement that demographic pressure has reached its threshold. Early beekeepers who learned to read that announcement and who responded with space, selective cell management, and timely splits were not suppressing the biology of the colony. They were working within it, converting the colony's reproductive momentum into a managed outcome aligned with apiary productivity. The bees have not changed. Their preparation sequence runs the same today as it ran in the apiaries of Quinby and Dadant in the 1880s and 1890s. The window is still 72 hours. The queen cells still cap on day 8. The abdominal reduction of the laying queen still precedes departure. The swarm cohort still loads its honey stores in the hours before flight. The only variable is whether the beekeeper is present, observant, and prepared to act within the biological timeline rather than around it. If this breakdown was useful, leave a comment with your experience. Subscribe for more historically grounded beekeeping insights.